cement silo looks like a simple, upright vertical cylinder, right? Today I will dive deep into the design of this heavy equipment and I will decipher the complexity inside. I'm Dr. Ali Reza Islami, the former university professor, and welcome to my channel, Dr. E.
Dear followers, colleagues and friends, welcome. Today I'm incredibly excited to kick off the very first episode of our engineering series. We will design a 28-ton cement silo completely from scratch. Episode 1 is about the design of the 3-segment cylindrical shell. Follow along with me step by step and let's design for manufacturing together. Thanks a lot for watching and please follow me to the end of this video. Before we dive into the core engineering and SolidWorks modeling of our 28 tons silo, let's take a quick look at the detailed anatomy of a standard conventional cement silo. Understanding its primary components, auxiliary equipment, and integrated systems for operation, safety, maintenance, and environmental protection is vital before drawing a single line. In this slide, you can see the comprehensive schematic diagram. The primary structure core in the main cylindrical container or shell. This shell terminates at the bottom in a 60-degree conical hopper, an optimized angle desired for facilitate the smooth gravity extraction of stored cement powder. At the top, we have a roof deck with a gentle 5-degree slope, engineered to drain rainwater or melting snow toward the outer rims and away from the critical equipment. The entire structure is supported by 4 robust structural legs. These legs are securely welded to the base plate, which will be anchored into a concrete mat foundation pad in our final design. To maximize structural integrity against wind, seismic, or lateral shear loads, these legs are structurally tied together with cross bracings. We will dive deep into the calculations and the structural detailings of these elements in upcoming episodes. For material delivery, we have a dedicated pneumatic filling pipe. The lower intake terminates close to the ground floor, allowing standard bulk cement tanker trailers to easily hook up its pneumatic feeding system. The pipe runs vertically all the way to the top roof deck. Notice that it extends half a meter vertically inside the silo. This prolonged stem ensures that the incoming cement powder is delivered flawlessly down into the center of the container, reducing wall abrasion. Because the silo is filled via high-pressure air streams, we must safely vent the entrapped pneumatic air into the atmosphere. However, this escaping air carries a dense cloud of fine cement dust. To prevent environmental contamination, an air filtration unit is installed directly on the central axis of the roof deck. Depending on your operational preferences and budget, you can deploy a mechanical shake system using cylindrical cartridge filters or a pulse jet air filtration system that utilizes compressed air pulses to clean flat envelope filters. Regardless of the type, the captured dust falls right back down into the silo, preventing material waste. We will explore these filter operations in details later in this series. For safe preventing maintenance, inspection, and filter replacement, an external climbing ladder equipped with a safety cage and guardrail is fully integrated into the outer wall of the silo. Furthermore, a dual-acting pressure relief valve is installed on the roof deck. This valve acts as a critical safety barrier, compensating for both over and under pressure during pneumatic filling and vacuum. Under pressure during material extraction happens. Next to it, a level sensor is mounted to monitor the exact filling height and prevent overfill scenarios. Moving down to the conical hopper, you will notice a series of fluidization pads commonly referred to as aerator mushrooms. In a silo of this scale, we typically install a ring of 4 fluidization pads spaced evenly at 90-degree intervals around the lower third of the cone. These pads feature an internal air jet element that injects low-pressure, high-volume compressed air directly into the bottom of the silo. This action aerates the cement, creating a temporary fluidized bed that drastically reduces friction. This layout is absolutely critical to eliminate common material flow obstructions such as rat holing or bridging during discharge. The lower discharge flange of this cone connects directly to a high-performance butterfly valve, which acts as the primary isolation barrier. Below the valve sits a screw conveyor, which mechanically extracts the fluidized cement powder and transfers it to its destination, such as a weighing hopper positions right over a concrete mixer. Finally, there are secondary but vital details like inspection manholes, handholds, sight glasses, temperature and humidity sensors, and localized electrical control enclosures. We will dive deep into selecting the most cost-effective and operationally viable configurations of these components as our project advances. Now you might be wondering why I chose exactly 28 tons as our target capacity for this project. The answer lies in logistics and supply chain optimization. In most international and regional transportation sectors, the standard 3-axis or 4-axis bulk cement tankers carries a net payload ranging between 24 and 26 tons of loose powder due to strict gross vehicle weight limits. By designing our silo for a net capacity of 28 tons, we are optimizing it to comfortably accept one full standard truckload with an engineered buffer margin. Great, now with our capacity target set, let's calculate our required internal volume based on material characteristics. The loose bulk density of cement is roughly 1.25 cubic meter, a value driven by the air entrapped during pneumatic handling. To hold a net weight of 28 tons, we require a minimum net powder volume of approximately 22.4 cubic meter. However, we cannot fill a silo completely to the brim. We must apply a standard 12% safety freeboard factor at the top. This expansion space accommodates the air filtration unit's internal clearance, the incoming pneumatic stream, and high-level pressure switches. Incorporating this factor brings our total required internal volume to exactly 25.1 cubic meter. Setting the silo's maximum payload capacity to 28 tons creates the ideal single truck storage solution. It provides a built-in 2 to 4 ton volumetric buffer, which amounts to roughly a 10 to 15% safety margin. This ensures that when a delivery truck pumps its entire load under high pneumatic pressure, you run zero risk of overfilling the storage tank, triggering high-level alarm, or choking the top venting filter with compressed powder. It is also critical to cross-check our calculated dimensions with commercial market standards to ensure compatibility with the standard logistics, load transportation rules, and off-the-shelf spare parts. According to industrial metrics, the standard 25 cubic meter hopper bottom silo is officially classified by manufacturers as a 28 to 30 ton capacity unit. This means our custom configuration maps perfectly onto high-volume commercial manufacturing lines, allowing us to utilize standard fabrication techniques and substantially minimize tooling and material costs. Now is the time to establish our primary geometric constraints. One of the most critical dimensions is the external diameter of the cylindrical shell. For our design, an outer diameter of 2,500 mm or 2.5 meter is the absolute golden number. This specific dimension allows the fully fabricated silo shell to fit neatly within the standard flatbed truck dimensions. For horizontal road transport, it completely avoids the need for expensive, time-consuming, oversized cargo permits or specialized escort vehicles. Perfect. Now that our 2.5 meter diameter is locked in along with our 60-degree conical bottom, standard 300 mm outlet flange, and the 5-degree roof deck slope, the exact mathematical height needed for the cylindrical section is 4,215 mm. However, as an engineer designing for manufacturing, I am rounding this number up to 4,500 mm. Why? Because the standard market width for hot rolled steel coils and sheets is precisely 1,500 millimeters. By setting our height to 4,500 millimeters, we can build our shell using exactly 3 rings of 1,500 millimeters each. This clever adjustment gives us a bit of bonus storage volume while completely eliminating the need for plasma or gas cutting. Reducing the labor and achieving zero material waste are other bonus we can expect. Great! Now we can review the comprehensive layout of our primary dimensions on this slide. To summarize, we have an outer diameter of 2,500 mm, a total cylindrical shell height of 4,500 mm, a roof deck height of almost 66 mm, a 60-degree conical hopper height of approximately 1,900 mm, and a ground clearance of 1,500 mm from the foundation level to the discharge opening. For the cylindrical shell section, we must select the most viable material type and the stock form. In SolidWorks, I have assigned ASTM A36, which is structurally equivalent to ST37. This structural carbon steel offers exceptional workability for plasma cutting, edge grinding, plate rolling, and welding, while remaining highly economical. It features a minimum yielding strength of 235 megapascals, which easily withstands static and dynamic outdoor loads when using a robust 5 mm plate thickness. Furthermore, instead of using flat metal sheets, which come in restrictive 3, 6, or 9 meter lengths, we are basing our production on hot roll steel coils, which arrive in bulk loads of 15 to 25 tons. This allows us to decoil the exact circumferences lengths of roughly 7.85 meters per ring, grind the edges, and roll them. Another hidden advantage of hot rolled coil steel is its inherent coil memory. Because it is already stored in a curved state, rolling it back into a perfectly uniform cylinder is vastly easier than trying to roll stiff flat sheets. Perfect. Now that our dimensions are verified, we can establish the fabrication parameters for the shell rings. Let's talk about rolling and weld prep. We include an extra 50 mm flat allowance on both ends of our plate lengths during the initial rolling phase to avoid the common flat end artifact caused by the flat rolling machines. Once rolled, these flat margins are trimmed off to ensure a perfectly rounded circle where the longitudinal seam meets. For the primary structural welds, we must apply a bevel grind to allow joining edges. As shown in the detailed drawing, we are utilizing a 60-degree single V-groove weld with a 1.5 mm root land and a 1.5 mm root gap. The root land is critical for controlling heat dissipation and ensuring uniform weld pool flow during our gas melt arc welding or MIG welding if you're using MIG welding. The 1.5 mm root gap ensures that our weld achieves complete joint penetration across the full 5 mm plate thickness from the outer face to the inner root. Once our rolled rings are aligned for welding, we execute a precise tack welding sequences starting from one end and moving across the seam. It is critical that the first tack welds are placed at least 50 to 100 mm away from the absolute edges of the plate. Placing tacks directly on the edge can cause severe localized thermal distortions, microcracking, or edge burn through. We will repeat these tack welds every 200 to 250 mm along the seam, with each individual tack measuring roughly 20 to 30 mm in length to securely hold the joint alignment before the main welding process starts. Great! Another vital structural rule in pressure vessel and silo manufacturing is the maximum distance between the vertical weld seams of consecutive rings. Stacking vertical welds creates a continuous weak line highly susceptible to stress concentration. To prevent this, we stagger each successive ring by 120-degree angular offset during assembly, ensuring that no two vertical seams align. Great! Now that we have established all our structure and manufacturing parameters, we are ready to build the model in SolidWorks. For this series, I'm assuming you already possess a foundational working knowledge of SolidWorks, so we will skip the basic UI explanations and jump straight into drafting. We first begin by opening a new part file and selecting the top plane as our primary sketch plane. We draw a circle centered directly on the coordinate origin and use the smart dimension tools to lock its diameter at exactly 2500 millimeters. Next, we transition to the Features tab and execute the Extruded Boss or Base command. By activating the Thin feature option and selecting it to extrude inward, we instantly create a hollow cylinder with a height of 1500 millimeters and a precise wall thickness of 5 millimeters. To replicate the physical manufacturing gap required for our weld joint, we must cut a seam into the solid cylinder. I'm sketching a narrow rectangle on the front plane that is exactly 1.5 millimeters wide. I will set its length to 1400 millimeters, which easily clears the radius of our cylinder, and use geometrical relations to ensure it is perfectly symmetrical about our central plane to avoid any thin feature rebuild error. With the sketch active, we apply an extrude cut feature, setting the end condition to through all. This cleanly removes the material, allowing the entire 1500 millimeters vertical height of our shell ring. Here I'm using the Evaluate Measure tool to cross-check our work. As you can see on the screen, the distance between the cut faces measures exactly 1.5 millimeters, providing the precise root gap we discussed during our fabrication planning phase. Perfect. Now let's add our structural weld prep. I have applied a mint green appearance to the shell to make visualization easier. Next, we select the chamfer tool and apply it to the outer vertical edges of our open seam. We set the chamfer parameters to an angle of 30 degrees relative to the face normal with a distance of 1.75 millimeters. This precise geometry preserves our required 1.5 millimeter root length along the center of the 5 millimeters plate edge. We repeat this identical chamfer command on the remaining vertical edges of the gap. Since we have both internal and external weld prep considerations for full penetration, we apply this to all for vertical boundary lines. This close-up shot gives you an excellent visualization of how our joint preparations looks in 3D. This pristine 60-degree V-groove is exactly what the fabricators will see on the floor shop before initiating the MIG welding process. Let's take a step back and switch to a trimetric long-shot view of our progress. The first ring of our cylindrical shell is now geometrically complete and optimized for rolling and welding. Next, we must apply the same beveling and chamfering to the top and bottom circular rims of the shell ring. This ensures that when the rings are stacked on top of each other or when they connect to the top roof deck and bottom cone, we maintain the exact same 1.5 millimeter root length and weld penetration capabilities across our horizontal seams. This perspective view shows our completed single ring. Now we navigate to the Feature Manager design tree, right-click Material, and assign ASTM A36 steel to the part. By opening the Mass Properties Evaluator, we can verify that the calculated physical weight of a single ring is precisely 463 kilograms. Perfect! We are down to the final step of our first episode. Stacking our rings, we open a new SolidWorks assembly environment, we import our first ring, right-click to change its status from fixed to float, and use the Mate tool to align the origin of the first ring perfectly with the origin of the assembly file that will lock it in place. Next, we import the second ring, we apply a concentric mate between the two cylinder bodies, and then apply an angular mate of 120 degrees between their perspective front planes to achieve our weld seam stagger. To guarantee our horizontal 1.5 mm weld gap is modeled accurately, we apply a distance mate between the reference planes of the two rings by setting the distance between their primary horizontal reference planes to exactly 1500 1.5 mm. This way, we leave a perfect uniform 1.5 mm gap for the horizontal weld beads. This is how our assembly looks with the first two rings mated. Notice that the vertical weld seams are cleanly offset by 120 degrees, and this drastically improves the structural load path of our shell. Let's keep moving and bring in our third and final shell ring. We apply the exact same concentric and vertical distance mate to position it cleanly on top of the second ring. The only difference for this third ring is its orientation. We apply an angular mate of 240 degrees between the front plane of the first ring and the third ring. Now all three longitudinal weld lines are perfectly distributed around the perimeter of the silo shell. To wrap up today's session, I have brought a simple custom-scale human mannequin into the assembly to give us an immediate sense of scale. What you see on the screen is the completed manufacturing-ready cylindrical shell of our 28-ton cement silo. This concludes our first episode. Thank you all so much for your time and attention, and see you in the next episode.
If you're a manufacturer, an engineering student, or an industrial designer who wants to analyze, simulate, or modify the 3D CAD model that we built today together, please just hit the subscribe button and comment the word CAD below. You will receive the link to download it. Please also comment what is the next equipment you want to see engineered. Thank you very much for engineering with me today. I'm Dr. E, and see you in the next breakdown.